All right, so we've got this region bounded by these two functions. That upper function there is the cosine function. The lower function is the quadratic. It's an upright quadratic, so you can see that there. First of all, they want me to find the area of region R. Okay, areas are very simple. They're based off the idea of Riemann sums. So if you imagine drawing a rectangle in there, the area of a rectangle is length times width, or base times height. You can write a dA statement. It's the change in A as you move from one of these little rectangles to another. The width of the little rectangle is horizontal in this case, so that's going to be a dx, an infinitely small horizontal change. The length of a side there is, you can see you have an upper value minus a lower value. It's vertical. So you can call this point x comma y2. We have another point down here. You're always putting points on the curves because you're trying to tie into the curve. This is the point x comma y1. So we have the same x coordinates, but we have different y's. So to find the height, you take the upper minus the lower. Even if it's negative, it would just be minus a negative, but we don't have that issue here. So that's y2 minus y1. And you write everything in terms of whatever variable you have here. So if this is a dx, everything's written in terms of x, which I do have in this case. y2 is my cosine equation. It's the upper equation. y1 is the parabola equation. So the integral here, basically I'm just going to take that statement and turn that into an integral. The integral will add up the areas of those rectangles as they change. We're going from x value of 0 over to 2. And we're going to do y2 minus y1, but we're going to write it in terms of x. So y2 is that 4 cosine of 1/4 pi x. So y2 minus y1. Make sure you have parentheses on this because it's a sum and difference. And anyway, it's basically just the upper function minus the lower function. Take the integral over that interval. Technically, you should have a dx with all of this, like my formula says. And anyway, that should work out quite nicely. Now, this particular problem is supposed to be done using the Fundamental Theorem. It's kind of a long one for that, but just for the heck of it, let's go ahead and do that. If we integrate here, it'll be a sine function. Inside function won't change. The derivative of the inside function is 1/4 pi. So I need a 4 over pi on the outside to counteract for the derivative of the inside function. And then, of course, it was originally a 4 cosine, so I'm going to have a 4 out in front as well. And then over here it's going to be minus, I'm going to distribute here, that's minus 2/3 x cubed. Be careful here, minus negative is a plus. So that's going to be plus 3x squared minus a positive, that's going to be minus 4x. Okay, and again, we're evaluating this between 0 and 2. Actually, if you put 0 in here, sine of 0 is 0, so everything is going to cancel for the 0 term, so we really just need to evaluate this at 2. Anyway, if I evaluate it at 2 here, that's going to be sine of pi over 2. Oops, I'm out of focus here. Let's see if we can get it back. Okay, that's going to be sine of pi over 2. Sine of pi over 2 is just equal to 1. So I'm basically going to get just 16 over pi for that first part. And then, let's see, if x is equal to 2 here, 2 cubed is 8, it's going to be minus 16/3. And then 2 squared is 4 times 3 is 12, so plus 12. And then minus 4 times 2 is minus 8. And that should simplify down to just 16 pi minus 4/3 if you go through the whole simplification process. Again, I believe you can actually leave this form here, but anyway, that's the better form of the answer. Okay, so big thing is you're just taking an integral of an upper function minus a lower function. That's how you find the area, as long as you always have the same function on top and the same function on the bottom. If one of the functions changed, you might have to do one integral with the first upper and the it's lower, and then switch to another set of functions. Or you might have to do it from right to left with horizontal strips. It's another possibility, but that's what's going on in Part A. Part B says write, but do not evaluate, so it's going to save us some time, an integral expression that gives the volume of the solid generated when R is rotated around the horizontal line y equals 4. Okay? So if we go look up here, y equals 4 is this horizontal line right here. Okay? It's going to be rotated around that, and so we're basically going to get an image. This drawing is probably going to be hideous, but let's see what we can do here. And get an image that looks kind of like that. And when we rotate this thing around, basically what's going to happen is you're going to have this kind of outer bell-shaped type region, and then you're going to have this inner region that gets removed from here when this thing is rotated around. Okay? You can draw gorgeous pictures of this, but the important thing is it's really just an outer volume minus an inner volume. And so I really just want to find the volume using this function here, which is the cosine function, and then subtract the volume of the other one. So the formula that I use for this, remember that we're going to cut this into disks. This is a disk method problem. So we're taking the integral of pi big R squared h, that's the big radius, the outer function, and then we're going to subtract the inner volume, pi little r squared h, the little radius. And both these should match up pretty similarly. So anyway, if we go back up here and we look at this, the big outer radius, actually let me do this in a different color. The big outer radius will basically have a circle that looks like this. The radius is going to go from the axis of rotation. Remember, that's the line y equals 4. That's going to go out here. Now, the one thing I need to be careful about, this is the reflection of the original function. I really want everything based on the original function. So when I'm drawing my radius really needs to come down here and come to that point x comma y. Also, this disk will have just a little bit of a width. So again, that is a cylinder. It's a very large circular cylinder with a very small height. Notice I have a small height. That's a very small change in the x direction, so that's a dx. Okay, so down here, the height of my disk is going to be a dx. If you go back and look at the radius, remember you need to go from the center back to the original function. That's a y value minus another y value. You subtract y values to get a length there of a radius. So that y value is 4. This y value is the is function f, the 2x squared equation. So it's going to be 4 minus that 2x squared equation. So we're just going to call that 4 minus y for the time being. And notice this all needs to be written in terms of x, so I need to rewrite that y in terms of x. And also, my bounds are going to be in terms of x. Everything is in terms of x. So if you go look at this, we're going from an x value of 0 to an x value of 2 for that outer function. So let's put all this together now. So here we go. I'm going to factor the pi out. And the radius is 4 minus the y value. The y value, again, is 2x squared minus 6x plus 4. Okay, the whole radius, that whole thing, is being squared according to the formula, and then multiplied by dx. The x values go from 0 to 2. Okay, so that's our outer volume. We're now going to subtract the inner volume, and that's going to be pi little r squared h, and that's basically going to set up the same way. If you go back up here and look, it's a little hard to see in this diagram at this point, but basically what we're going to have here is you have a little circle on the inside that's being cut out, and you want the radius of that little circle. So once again, your radius there is going from 4 down to this point here. It's going to be 4 minus that y coordinate, but that y coordinate is coming from this curve, which is the cosine function. So you're just jumping functions there. You're now using the inner function. So it's the same thing. I'm going to factor the pi out, and it's going to be 4 minus the y value. But again, the y value is really that 4 cosine of 1/4 pi x. So I don't know why I wrote that down there, but right, that is minus 4 times the cosine of 1/4 pi x. And that whole thing is being subtracted from 4. Remember that the radius needs to be squared, so this whole thing is squared. And again, the width of this whole thing is a little horizontal change there. That's a dx. So we have a dx. Bounds are going to go from 0 to 2, just like the other one. Okay, so that's what's going on there. They're not super easy to set up. However, if you practice this a little bit, I actually think these are really nice problems to pretty much guarantee yourself about 6 points, because there's just not that much unexpected that happens in these problems. So maybe some of the least fun to do, but also some of the probably most easily guaranteed points. Okay, and we go down the last part. Unfortunately, I've messed my picture up here, but it says that the region R is the base of a solid. Each cross-section perpendicular to the x-axis is a square, right, but do not evaluate an integral expression that gives the volume of the solid. Okay, so I'm going to have to freehand this because I've messed up my diagram now. But basically, we have this region here that's doing, you know, this kind of thing over to 2. And they're saying that the cross sections are squares perpendicular to the axis. So basically we have these squares that are coming through with this height. They're actually coming out like from the paper at us, but that's hard to draw. So I'm going to do this kind of perspective thing here and show one of those squares coming out like that. Notice it goes from one curve down to the other curve. Okay, this is sometimes called the slab method. These little squares should have just a little bit of thickness, and so it'll look something kind of like that. And again, it's sometimes hard to kind of imagine what these really look like, but these are very easy problems to do, because the only thing you need to do is change from the integral of pi r squared h to an integral of the formula for the volume of that square prism. And if you notice, the volume of a square prism, no, I wouldn't have thickness there, but anyway, basically you have, I'll call that the width, and I'll call that the side length, and so the volume, we can call that dv. That's the change in the volume as you move from one slice to the next. It's just s squared times w, or s squared times the thickness, or s squared times the height, whatever you want to call that. Well, if you notice, the side is still vertical. It's just a y-coordinate here minus a y-coordinate there. So it's going to be a y2 minus a y1. Again, the width here is an x, and so this is going to be dx. The side lengths need to be in terms of x. It's going to be y2 minus y1, and it's squared. And we'll just write everything in terms of x. Make sure you have the right function on top. That's the cosine function. So it's going to be the integral of, again, from 0 to 2. There's no pi this time. The upper function is function g, which is 4 cosine of 1/4 pi x, okay, minus the lower function. It's the whole lower function, so I need that in parentheses. Okay, that whole side length, y2 minus y1, is squared and then multiplied by dx. And so you end up with that final function there, and that ends up being all you need to do.